Let's do another example. Again, it's a 2 by 2 matrix. We should be able to go through the same procedure. We subtract off lambda from the diagonal. We recall that we need to look for the determinant of the matrix. So for this, that is the determinant. That times that minus this times that. That we call the determinant of that matrix. If we go and we simplify that, we get this. So let's have a look at that more carefully. Here I'm just repeating what we just said. And we end up with this equation right here. And this time I'm having some trouble seeing what the factors are, so I'm going to use the quadratic equation. Remember that if you have a times x squared plus b times x plus c equals 0, then the roots are given by x equals minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. Now in this particular case a is 1, so we can strike that out. And if you then plug in the coefficients for this particular quadratic equation, you end up with this right here. Now the unfortunate part is that this here is 16 minus 20 is equal to minus 4. And you might say, well, then it doesn't have real roots. We're in trouble. Well, that just goes to show that a matrix with real valued elements can have complex valued eigenvalues. So in this particular case, the eigenvalues are this right here, which you can write as 2 plus or minus I. And notice that this is an imaginary number. It's perfectly okay for a matrix to have imaginary eigenvalues. Yikes, of course. And we're going to try to sort of avoid the case where matrices have complex eigenvalues, although we'll talk about this a little bit more later. So in this particular case, let's go ahead and push it through. If you then take your eigenvalue to be 2 plus I, you plug that in right there. You then look for a vector that satisfies this, where maybe for clarity I should put some lines in here. And if you then ask the question, what non-zero vector lies in the null space of that matrix? Well, let's not concern ourselves with that too much. All I know is that there will be complex valued entries in that vector. And if you then do the same thing for the other eigenvalue, then again, you get some vector which will have complex values as coefficients in the null space, which then becomes the eigenvector associated with this eigenvalue. Okay, so we had some trouble figuring out what the eigenvectors were for this particular non-symmetric matrix, and the reason was that its eigenvalues were complex. Well, why don't we just instead visualize it, and we'll just see when the two vectors point in the same direction, and when they do, we know we've got an eigenvector. So let's have a look. Good, X is catching up the blue one. Wait, they're starting to spread out again. But we want them to point in the same direction. Alright, X is catching up again. But it doesn't. So what's going on here? Well, the fact is that there are no eigenvectors that are real valued. So in order to be able to visualize the eigenvectors for this particular matrix, we would have to visualize the complex plane. But wait a minute, if you want to look at a complex number, then you need the complex plane to visualize that. So if we now have a vector with two complex values for its coefficients, we would have to be able to visualize this in 4 dimensions. And obviously we'd have a rough time doing that. So the fact is that when the matrix has only complex eigenvalues, then you cannot visualize the eigenvectors in the 2D plane here. Okay, so to summarize, if you want to find an eigenpair for ax equals lambda x, and notice that what our animations showed was that what this really means is we're looking for vectors x that are in a direction such that the action of matrix A is exactly the same as scaling that vector. That's what we're looking for. What you do is you find the roots of the determinant of A minus lambda I, set to 0. Each of those roots then becomes an eigenvalue, and for each of those eigenvalues you then find vectors in the null space of A minus lambda I.